In the second video on applying Newton's second law to rotation problems, we have a compound pulley. This is a pulley in which a bigger pulley has been attached to a smaller pulley. They may have welded them together or some other attached them. And it's got a shaft right here in the middle that's holding it up with an axle. There are two strings pulling on this. One's pulling horizontally at 10 newtons, one's pulling down at 12 newtons. And we've been given their radiuses, their total mass, and we're asked what is the pulley's angular acceleration. Well, like any other type of problem, when you see the word acceleration, you're thinking drawing a free body diagram. So let me draw a free body diagram. I've almost got one up here, but I don't have the pulley, the axle force. So I'll just draw that. That's the axle pointing the y direction, and here's the component of the axle force pointing in the x direction. I also need to put in the weight force. There's definitely weight on this pulley, and that would be pulling down. So I put the weight, I applied the apply. There is no normal. There are two tensions. You can call this one T1 and you can call this one T2, and there's no friction. So weight applied, normal, tension, friction. In terms of x and y, I need a coordinate system. There's x, there's y, and I need a direction of positive torque. I'll choose at this time to go that direction. Critical angles and dimensions. There is a critical angle, this angle, to break this vector T2 up into parts. And there are two critical dimensions. One of them is this dimension right here, which I'll call R1. And the second critical dimension is the dimension here, which I'll call R2, which is needed to calculate that torque. Alright, that's all the critical angles and dimensions. So, free body diagrams, same way we did them since the beginning of the course. Isolate the body. Inventory the forces using Watt F. Weight, applied, normal, tension, friction. If you have an axle or some sort, break that force into two components, an x part and a y part. Makes the trig and math easier. Then draw an axis, now with appropriate torque, positive direction. And last but not least, identify all critical angles needed to break the vectors into components and all critical dimensions needed to calculate torques. Define the torque about this point in the center. We know we're going to need that. We know we're going to need the center of the moment of inertia about that times alpha. Now the center of inertia here is going to be the inertia for pulley 1 and pulley 2. And we're going to need to know something else that I didn't get told. So we need to know something, and I wasn't told it. I was only told the total mass, so there's a problem. This problem needs something else. Assume that M1, M big pulley, is 6 kilograms, and then M little is 4 kilograms. They should have given me separately the masses of the pulley to work this problem. So I've got one pulley, mass 1 times radius 1 squared times 1/2. That's the moment of inertia of a pulley. And 1/2 mass of the second pulley times radius 2 squared. So calculating the pulley here, it's equal to 1/2 times 4 kilograms times 2 meters, which were squared. The bigger pulley was 6 kilograms. Its radius was 4 meters, and I need to square that. And then I need to punch the calculator to find the effective moment of inertia. So let's see, 4 times 4 divided by 2, that's 8 for the little one, plus 16 times 3, total is 56. So the total moment of inertia is 56 kilogram meters squared. So Took advantage of my knowledge of tables from Giancoli or whatever book you're using to find the little pulley. So that's how I get these formulas. I needed to know their individual masses and their total R's in order to calculate the thing. The total weight, well, that's just going to be their sum, 6 and 4 times 10, but I needed their individual ones here to calculate the moment of inertia. Now to calculate the torques, on the left-hand side, I remind you that for any rope on a pulley, it's just TR. So the first one I have is T1R, and it's in the minus direction. And that's distance is R1. And for this one out here, it's plus T2R2. And that's going to be equal to IC times alpha. Now, what about all these other forces? This force here, this force here, this weight. They have no moment arm because they're applied at the axle. So they produce no torques. So looking at this, I have minus 10 newtons times 2 meters plus 12 newtons times 4 meters is approximately equal to 56 kilogram meters squared times alpha. And by alpha, we mean that this is the direction of positive alpha. So we got minus 20 plus 48 would give us 28 Newton meters, and that's approximately 56 kilogram meters squared times alpha. So alpha is 28 divided by 56, which looks like it came out to be a nice number, just amazingly. It did. Certainly was not intended to. 2.00 rad per second squared. What does that mean? That does not mean it's spinning clockwise, but it does mean that that's the direction of the rotation's acceleration, angular acceleration. So if it's spinning this away, it'll be slowing down. If it's spinning that away, then the acceleration's in the same direction, it's speeding up. Okay? Not the same thing as velocity. Acceleration tells us how things are changing. What about the force applied by the axle upon the pulley? Well, the pulley wasn't going anywhere, so we know that the sum of the forces in X is equal to the mass of the pulley times the acceleration in X, but it wasn't accelerating. And the sum of the forces in Y is the mass of the pulley times the acceleration of the pulley, but the pulley was rotating. It wasn't accelerating in the sense that the center mass was moving. Notice we're talking about the center mass. That's what we're talking about, the acceleration, not the individual particles on the wheel. Now the forces, there were a bunch of them. We had the axle AY up, AX is horizontal, T1, and we have a T2 component. So let's see, we have T1 plus AX minus T2 times the cosine of an angle. That angle was 40 degrees. We're looking at cosine, this side, and it's in the negative direction. And that's 0. So AX was equal to minus T1 plus T2 cosine 40 degrees. So AX would be approximately minus T1. We have to go find what T1 was. That was 10 newtons. T2 was 12 newtons times the cosine of 40 degrees. So AX is approximately 10 it's minus 0.807 newtons. On the y direction, we had a minus W, we had a plus AY, And then we had a component of T2, this component going down here, which is the opposite side, right? So this right there would require the sine function. So minus T2 sine 40, and that's 0. So AY would equal M1 plus M2 times G, the total mass, plus T2 sine of 40. So AY would be, let's see, it was 10 kilograms times 9.8 meters per second squared plus 12 newtons sine 40. So AY is approximately 106 newtons, roughly. Now what does that mean? It means that the axle, if we draw this axle here, this force has got 106 newtons that away and 0.0807 newtons that away. So of course the value should be ax squared plus ay squared, but this is so much bigger that the magnitude is just about approximately ay, which is approximately 106 newtons. We also need this angle, and in fact really going all the way back over to that angle, theta. To find phi, that's the inverse tangent of 0.807 newtons over 106 newtons, which is going to be a very small angle. .436 degrees. So theta is 90 plus phi, so it's about 90.4 degrees. So the axial force is almost straight up. It's 106 newtons at 90.4 degrees. So that's the axial force. So it has to hold 106 newtons. If it can't handle that, then the axle will break. So it's, if you would, just barely, that's exaggerated, drawn like that. Okay? I wouldn't draw that on my free body diagram, of course, but that's to just tell you what it is. All right, that finishes this example.